Hey everyone, welcome to Birch Talks, where we break down important topics in the science, law, and policy of climate change, decarbonization, and renewables. We're doing our best to help make the future of our world just a little bit more accessible. I'm your host, Matt Chalmers, science nerd, environmental attorney, and founder of Birch Citadel. Let's get into it. Today, we're going to be talking about methods and data that go into analysis of extreme weather events in the IPCC AR6. So ever since the release of the fifth assessment report, or AR5, our understanding of weather and climate extremes has advanced significantly, thanks to improved climate models and a better grasp of the different physical and scientific processes that are driving these changes in our world. We can now predict extreme weather events with way more confidence and precision. Welcome to this deep dive on how our knowledge of climate extremes has progressed since AR5. Whether you're interested in tracking heat waves, floods, or severe storms, this video should provide a relatively comprehensive introduction on the latest science for folks that are interested in climate change and climate modeling at a deeper level. You may have heard a great deal about climate models if you're interested at all in the future of our world. It's a topic that we see appear in news media, in YouTube videos, even on TikTok, all over the place. Climate models are predicting this if we don't implement this policy. Climate models are predicting this. But, well, hold on. Just what is a climate model? How does it work? Why does it work the way that it does? And why are we confident in whatever results they're spitting out? These are questions that I run into all the time when I'm talking with ordinary folks about the future of our world. So I figure let's get into it and help demystify this really nerdy, fun topic just a little bit. So where do we begin on climate models? Our world is such a complex system that there are innumerable different fields, different theories, different scientific equations that can be used to describe our world. So the complexity of our climate system has been a huge challenge for scientists for decades. In order to understand anything that's complex, typically what we want to try and do is something that's called analysis. We want to take something complex and break it down into each one of its constituent component parts so that they're a little bit more manageable and we can understand it. And anything that's too complex, you just keep analyzing it, breaking it down more and more and more and more until you understand each of those pieces. And then you put it back together. And the idea is now that you understand each component, you understand the whole of the thing. Well, climate change is similar to that, but it's a little bit trickier because you also have different synergies that occur systemically between each of these different components. So it's not enough to understand each piece in isolation. You also have to synthesize it all back together in a cohesive way so that all of those different interactions between the different components of the system are accurately reflected. The way that we tackle this in climate modeling is with something that's called a global climate model. So these models are massive, intricate mathematical equations that are then input into computer models. So basically what we're looking at is a whole set of math and a whole set of science that's running through code. And believe me, there is a lot of it. So although these have become absolutely indispensable in understanding the impacts of human activity on the climate and the future of our world, we're dealing with something pretty complicated. Specifically, we're dealing with a typical global climate model containing enough code to fill, let's say, 18,000 pages of text. It takes dozens, hundreds of scientists years to develop, improve, refine these models. These models run on supercomputers, and I want to emphasize, even with today's technology, the size of a tennis court, for example, the Cray XC40 at the UK's Met Office Hadley Centre. So these machines are capable of, brace yourself, 14,000 trillion calculations per second. From simulating regional climates to representing the whole Earth system, these models drive forward our understanding of climate change. They help inform policy decisions and have for decades. There's lots of different ways to handle the processing power behind this, whether it's single supercomputers or whether there's other networks of smaller computers. One of the things you can even do is join networks of smartphones or laptops or computers that when they're idle, donate some of their processor power around the world to running these kinds of supercomputers style simulations in a more distributed manner. The point is, these are intensely complex and rigorous models that run on a lot of code and take a lot of computational power in order to calculate all of those different interactions between all of the different mathematical representations of the science and the scientific principles that we understand about our world. So on that note, let's start talking about the physics behind climate models. So at their core, climate models are built on fundamental principles of physics. They simulate the interactions of our atmosphere, our oceans, ice, and land through equations. temperature, humidity, all of those different kinds of factors, fluid dynamics are all expressed mathematically. So in the same way in, for example, your high school science class, you're going through a textbook and you're having to memorize and learn how these different equations are used. Well, this is where those equations are used. There's just a lot of them. So for example, the first law of thermodynamics reminds us that all of the energy in a closed system can't be created or destroyed, only transferred. So that model might be working with, for example, a computational fluid dynamics model that looks at, well, how is that physical factor, how is that law of physics, that principle of our natural world, going to impact with this other principle and inform us how extreme weather events like hurricanes, which has been on many of our minds lately, especially in the southeastern United States, how is that going to affect the way that hurricanes form when there's more energy in the system? We can then plug that into more specialized equations that tell us, hey, we think we're going to see more hurricanes that are probably going to be more energetic as a result of how we understand, for example, there's more heat in the ocean that's underneath the hurricane as it's moving across. And because that energy can't be created or destroyed, that energy's got to go somewhere. And we know where that energy is going to go. It's going to go probably into that hurricane. And probably the hurricane is going to get stronger and more destructive as a result. So another essential principle is the Stefan-Boltzmann law, which helps explain Earth's natural greenhouse effect. Meanwhile, the Navier-Stokes equations describe the movement of fluids, whether it's gases in the atmosphere or water in the ocean. To everyone who's watching who is a climate scientist, who is sitting here chuckling at the simple examples that I'm offering here, trust me, I understand and I hear you. But one of the things we're trying to do here, even if it's a little bit oversimplified, is make this as accessible to as many people as possible. As always, if there's anything that I've got wrong or mischaracterized, please let me know. I always want to make sure that we're putting the most accurate information we can out. Feel free to leave a comment below or a correction in the comment below, and we'll make sure that gets pinned. All right. So let's now jump into the code behind the models. So remember those 18,000 pages. Translating these physical principles into a model requires millions of lines of computer code, and that's often after you've optimized it. So most global climate models actually use a programming language called Fortran, which was developed in the 1950s. So while newer languages like Python, C, and others are increasingly used for specific tasks and might be more familiar to modern software engineers and programmers, Fortran remains dominant simply because of its speed on supercomputers. So now let's talk about spatial resolution and time steps. Okay, so when we're talking about global climate models, this is really important. In the same way that you can summarize a book in a sentence, in a page, in 20 pages, or 50 pages, the same thing is true for how much detail you want to put into a climate model. So one example is you could express the temperature of the entire planet in one relatively simple set of equations, but you're not going to get a lot of detail out of it. And so that's not going to be very useful. When we're talking about spatial resolution, what we're really talking about is, just like that book report, how much detail do you get into in the climate model? Different levels of detail are useful for different things. For example, if you want to look at effects that are happening in a very particular region, say 50 square miles or 20 square miles or 5 square miles, you're going to need, just like zooming in on Google Maps, a different kind of resolution of the science going into this model. So typically, the way that this is done is global climate models will divide the Earth into a grid of cells, calculating temperature, pressure, humidity, wind, and other factors. Each of these cells, remember, these are like pixels on a screen, have different layers that extend through the atmosphere and oceans. So now you don't just have pixels on a map of the globe that looks like this, but you can almost imagine tilting that resolution and seeing all of the different layers and components that are within each one of those pixels. So once you start getting into smaller, more detailed cells that have more layers, as you can imagine, this is going to take exponentially more computational power in order to solve all the different equations that are going into this global model. So just to give you a sense of this, increasing the resolution of a model by a factor of 2, so just doubling the resolution, requires an order of magnitude, roughly 10 times more computing power. So what this means is you've got a trade-off, and you have to be able to balance, hey, how much information do you need with how much time does it take to run the model? How much computational power is it going to take to run the model? How many different layers do you need to put into the model? What kind of information do you need out of it? Now it's starting to make sense that you might make some trade-offs and say, hey, maybe use that 50 square mile block instead of a 2 square mile block. just to give you an example of scale. So there's a whole other component to this too, which also exponentially increases the complexity, which is what are your time steps? In other words, what is the frequency at which the model calculates climate data? If you want seconds, good luck. We don't have a supercomputer that's capable of pumping that out in a useful time period, or at least not with a useful amount of data. All these different trade-offs need to be balanced in the models. So a 30-minute interval is common for atmospheric models, providing a compromise between detail and computational efficiency. Remember, as your high school science teacher might have told you, all models are wrong, some are useful. Global climate models is the art of trying to create a model that has the right amount of information so that we can get something useful out of it. All right, let's talk about emergent properties and model accuracy. So this goes right back to the notion of all models are wrong, some are useful. So this is where we're going to be talking about one of the most remarkable aspects of climate models, and this is their ability to produce emergent properties. These are complex patterns, storms, droughts, sea ice dynamics that are not explicitly coded into the model, but which will naturally emerge as a result of, assuming you've got your equations right and you've got all these different variables calculated correctly, the physics and the processes that are built into the model. So one of the ways it's helpful to think about this, and I understand there are folks that actually work on these climate models in the audience who might be cringing at how much of an oversimplification this is. Don't worry, I hear you. I had a lot of colleagues that worked on this, so I understand I'm oversimplifying a little bit here. But for everybody else in the audience who, like me, is not a scientist, it's a little bit like a football coach who's trying to figure out how to set up their team's formation. And you're not going to be able to control the exact outcome. You're not going to be a player out on the field, but you're giving everybody a general idea of what you want the play to look like. And everybody's generally going to have an idea about what to do on the field. Well, at least before the other team starts messing it all up. But in the same way, climate modelers and scientists can set the rules of the climate model. But then remember those emergent properties, the climate model itself is actually going to generate the patterns that we observe, such as the circulation in the oceans, carbon flows across the globe, temperature, pressure, fluid dynamics, all of those things. This is all going to be generated as a part of the simulation. And good news, the closer the simulation is able to generate the same kind of emergent properties that we actually see observationally in our real world, well, that helps give us confidence that the climate model is accurate. If you've ever watched Star Trek or any science fiction similar to that, it's kind of like saying, computer in the holodeck, build me a simulation of the Earth. That's really what we're trying to do. And the more accurate it is to our observations, then we have greater confidence that the model is accurate and all of the data that we're then able to extract out of it is accurate too. So let's take a moment and talk a little bit about the future of climate modeling. So as computing power continues to grow, especially given recent developments in AI, and looking out into the future, really exciting new spaces that are beginning to emerge in, for example, quantum computing, so will the accuracy and the resolution of our climate models continue to improve. Remember, all climate models are a trade-off between how much accuracy we want, how much information we want, how much time it's going to take to compute it, and how much computing power it's going to take to power these models. So as we get more resources and the ability to do more, we're going to be able to get higher resolution, faster updating models, and we're going to be able to see more emergent properties generated more accurately. So higher resolution models are now allowing us to simulate increasingly localized phenomena, giving us better insights into regional climate impacts and extreme weather events. So in the same way that we were talking about, hey, you've got a world and there's a grid of all these different cells, as those grids or those pixels are getting smaller and smaller, we're going to be able to have more useful information for, say, not just nations, not just subnational entities, but even regions, local governments, maybe even communities, as our computing power continues to improve. What this really says is the future of climate modeling is getting more accurate, it's getting more sensitive, it's getting more precise, and we're getting higher resolution, better data out of it faster. This is a really exciting time to be in the space. In the end, climate models remain one of the most powerful tools that we have for understanding the changing climate, and that will help us shape the policies that we need to in order to protect our planet for future generations. It's really difficult for us to understand where our world is going without these powerful analytic tools that take the best state-of-the-art science that we have and allow us to run these simulations, not just of what's happening now, but run simulations of what could happen later, depending on different policies, This is called scenario planning and is one of the most powerful outputs of our climate modeling capabilities as a species. Effectively, when we look at, for example, climate reports that say, hey, this is what we think is going to happen at 1.5 degrees of warming, at 2.5 degrees of warming, etc., what we're really saying is, hey, we've sat down and we've crunched those different scenarios, that different version of a future with all of these different temperature changes based on different policy outcomes, and we can predict with at least some degree of confidence what we think is going to happen, which basically is one of the good reasons why we probably ought to do something about this planetary fire that we've got. So let's now jump into advances in our confidence and understanding. So one of the most significant developments that we've had is the increased confidence that we now have as a result of modeling improvements in both the past and the future changes in climate extremes. So when I talk about climate extremes, what I'm really talking about are extreme events, how the bell curve has shifted statistically for things like temperature, hurricane speed, etc. The tails of those bell curves, where we see low probability, but very, very strong or very, very weak in a way that's unusual data, that's where we're going to be focusing today. So the increased confidence that we have in our understanding of those tails of the bell curves comes from multiple sources: improved physical understanding of the processes, a growing body of scientific peer-reviewed literature that integrates these various lines of evidence, and better accessibility as climate models are improving. So for example, reanalysis data sets that blend observations with climate models have become much more reliable, providing clearer insights into past extreme events, which we can then turn and use to fine-tune our predictions for the future. So let's now talk about climate models and temperature extremes specifically. So when it comes to temperature extremes, climate models have shown really strong capability. Globally and across most regions, our models, state-of-the-art models at least, can now pretty accurately reproduce the direction of changes that we've actually observed, whether it's increasing heat waves or more frequent hot days. Remember the tails of that bell curve. While there may be some discrepancies in the exact magnitude of these trends, the overall pattern is clear and generally accurate. And that's why we have high confidence in these model predictions as a general matter. So since AR5, the latest generation of climate models, such as those from the Coupled Model Intercomparison Project Phase 6, sorry, that's a mouthful, sometimes called CMIP6, have reinforced these findings. These models continue to accurately reflect global temperature extremes with improvements in resolution and in the processes that reflect the physical science. Let's talk about precipitation extremes and spatial distribution. This is a fancy way of saying where is stuff going to happen when it comes to precipitation extremes. So our understanding of precipitation extremes has been a particular area of significant advancement. So climate models have now been able to capture the large-scale distribution of extreme precipitation events over land with relatively high confidence. So this means that we're now in a better position to predict where extreme rainfall will occur, whether it's in the regions that are prone to monsoons or areas that are facing heavy storms. Importantly, some of these latest models are able to produce results that are also highly consistent with their predecessors, while also being more consistent with past records of observation. So when it comes to simulating the intensity and frequency of extreme precipitation, the fact that you are still consistent with predecessor models while improving accuracy is a really good sign that strengthens our confidence in the ability of these projections and their accuracy. So let's go ahead and talk about improved model resolution and topography. So one of the most exciting advancements that we've seen is in the higher horizontal resolution of climate models. So in other words, if you imagine a climate model is a picture of our world, imagine there's a grid, kind of like pixels on a screen. As those pixels get smaller and smaller, as the boxes of the grid get smaller and smaller, we're able to capture increasingly large amounts of fine-grained, high-resolution data about the world. So higher horizontal resolution is a fancy way of saying the size of those grid boxes are shrinking, the resolution is increasing. This allows models to do a better job of representing complex topographies, for example, mountainous regions, which are known to influence local climate extremes like heavy precipitation events. This is another one of those advancements that says, hey, the ability of our climate models to accurately paint these complex pictures is improving. So in regions that have highly variable topography, in other words, lots of mountains, it's not just flat, it's not just an ocean, this improved resolution translates to way more accurate forecasts of extreme events, allowing us to hopefully pinpoint the areas that are most at risk, maybe not necessarily for any one particular extreme weather event, but we can certainly better identify trends, patterns, and therefore inform risks, which can be invaluable to local communities. So, to summarize, a lot of these advancements in climate models and our understanding of the physical processes since the latest round of IPCC reports in the AR5 have really helped to increase our confidence in predicting these extremes, whether it's heat waves, extreme rainfall, other severe weather events like hurricanes, which have, of course, been on everybody's mind lately here in late 2024. These insights are crucial for policymakers, for infrastructure planning, for building design, for emergency management services, and for just climate resilient strategies in general across the globe and down at a regional and even local level. So as we move forward, integrating these advancements into real world decision making is going to be increasingly critical as we're working to live in a changing world and to thrive in a changing world. Thank you for joining us for this update. And I hope that this has helped demystify just a little bit of what's going on in the background and help make you more informed about the future of our world and how we understand it. Thank you so much, and I'll see you next time. Cheers.